Okay, chapter 3, we're going to do kind of out of order here. We're going to do 3-5, 3-3, 3-2, 3-1 for the most part, and then 3-4 last. So let's get right to it. Let's start with section 3-5. At this point, we should all be familiar to recognize the graphs of our functions. Recall the basic functions worksheet. So that's one that we went over a short while ago. Sometimes we're asked to graph a function that's almost like the one that we know how to graph. For example, suppose that we want to graph y equals x squared, which I've got, y equals x squared. But let's suppose that we've shifted y equal x squared down so many units. Okay, well, in order to know how to do that, you need to know how to work with transformations. That's the underlying cause there. Okay, so in my first example, suppose that we have the function h of x, which is equal to x squared minus 4, and I want us to graph h by hand. Using a table, and we'll just comment on what happened. Okay, so if x is 0, h is negative 4. Here's 0, negative 4. If x is 1, we get negative 3. Here's 1, negative 3. If x is negative 1, negative 1 squared is 1. Minus 3 is negative 3. Negative 1, negative 3. 2, 0, and negative 2, 0 are on the graph. So notice how the negative 4 is the reason for the shift downward 4 units. And that's what I did. I took this graph and I shifted it down 4 units. Okay. Let's graph k of x equals x minus 4 squared. Well, if x is 0, k of x is 16. That's way off the scale there that I've got. If x is 1, we get 9. That's about right here. If x is negative 1, that's way further off the scale that I've got there. So why don't we stick with positive numbers bigger than 1. If x is 2, 2 minus 4 is negative 2. Squared is negative 4. Here's 2, 4 on the graph. If x is 3, negative 1 squared is 1. Here's 3, 1 on the graph. If x is 4, 0, here's what I get. Here's 4, 0 on the graph. If x is 5, 5 minus 4 is 1. 1 squared is 1. And if x is 6, 6 minus 4 is 2. 2 squared is 4. And so there's 6, 4 on the graph. K of x is equal to x minus 4 squared. And notice how this graph means that I took the original graph of y equal x squared and I shifted to the right 4 units. To the right 4 units. Because of that minus 4, that's what caused that. Okay? So let's take a look at in general what's going on. Let f of x be one of the 8 basic functions on that sheet there. And let c be a real number. Item 1, if y is equal to f of x plus c, like we saw up here, where we just add a constant, you're going to shift the graph up or down, depending if c is positive or negative. If c is positive, you're going to shift your graph up. If c is negative, you're going to shift your graph down. If c is equal to 0, you've done no shifting at all. If you just added 0. Problem 2, y equals f of x plus c means that you're going to shift to the left if c is positive, and you shift to the right if c is a negative. And now this kind of switched, from how we'd want to think of it. We kind of tend to think c positive, I go to the right. C negative, I go to the left. But it switched on us. C positive means I go to the left. C negative means I go to the right. Okay, just like in this example, seeing negative means I go to the right 4 units. If f of x is equal to x plus 3 squared minus 4, let's comment on what's happening here. We're going to have to shift down 3 units, down 4 units, and to the left 3 units. Okay, so down 4 and to the left 3 means I'll be at the point -3, -4. And nothing else with the graph is gonna change, other than where it's located. I guess if we wanted to find the intercepts, we could do that. Set f of x equal to 0. Add 4 to both sides, and you can factor the left or take the square root of both sides. X plus 5 times x plus 1 equals 0 means that x equals -5 or x equals -1. There's -1 and there's -5 on the graph. If I wanted to find the y-intercepts, let x be 0, 9 minus 4 is 5, so 0, 5 would be on the graph. Okay, so here's another example. Same deal. Suppose that h of x is equal to negative the square root of x. Okay, I know that the square root of x contains 0, 0, 1, 0, 4, 2, and I'm looking at a half of a parabola facing outward towards the right in a quadrant 1. If x is 0, h is 0. If x is 1, h is -1. If x is 4, -2 is what I get. And if x is 9, -3 is what I get. Is 9, -3. Okay, so what's happening here is that we're starting off with a graph of y equal the square root of x, and we're going to rotate that into quadrant 4 because of that negative that's going on there. Suppose we have k of x equals the square root of -x. Well, let's see here. So the domain would be all non-positive numbers. Non-positive numbers. So if I let x be 0, that's okay. I get 0 is the answer. If x is -1, -1 gives me 1. The square root of 1 is 1. If x is -4, -4 is 4, so the square root of 4 is 2. The square root of 4 is -4 is 2. And if x is -9, there we go. If x is -9, we get -9, which is 9. Square root of 9 is 3. So here's -9, 3 on the graph. Okay, so what this curve is doing is it's in quadrant 2, and we're looking at a half of a parabola in quadrant 2. Of course, a complete parabola would fail the vertical line test and would not be a function. In general, let's let y equal f of x be one of the functions that are known to us on that sheet there. On problem 1, suppose that we have y equals -f of x, like up here. Okay. Well, in this one we had to rotate the graph about the x-axis. In general, we're going to have to reflect about the x-axis. Item 2, y equals f of -x means that we're going to have to reflect about the y-axis. Okay, in other words, my original graph is right here in quadrant 1. I'd have to reflect that into quadrant 2 with that x being replaced by a -x. Here's another one. Y equals negative the square root of -x. Okay, so the square root of negative x means that the negatives don't cancel out. I would have a graph in quadrant 3. Okay, the negative in front of the radical means I'd flip the graph over into quadrant 4. The negative underneath the radical means I'd flip the graph over into quadrant 3. So ultimately I have this graph in quadrant 3, and I've got some points labeled here. If x is 0, y is 0. If x is negative 1, the square root of negative 1 is, the square root of 1 is 1. I've got the negative in front of that, so negative 1 is the output. If x is negative 4, the square root of negative 4 means I've got 2, or negative 2 is the output. Okay? So next problem, h of x is equal to 2 times the absolute value of x, and k of x is equal to 1/2 times the absolute value of x. I'm going to graph h and k on both the same quadrant, and here are the x values I'm going to use. I'm also going to graph y equal f of x. Y equal f of x is the absolute value function. F of x equal the absolute value of x. And if x is 0, I get 0. If x is 1, I get 1. If x is negative 1, I get 1. If x is 2, I get 2. If x is negative 2, I get 2. And I've used those same values here in this table that I've got going on. And let's graph h of x and k of x. Okay, h of x is 2 times the absolute value of x. X being 0 means that 2 times 0 is 0. Okay. If x is 1, 2 times 1 is 1. 2 times 1 is 2. Excuse me. If x is negative 1, absolute value of negative 1 is positive 1. Times 2 is 2. If x is 2, 2 times 2 is 4. And if x is negative 2, the absolute value of negative 2 is positive 2 times 2 is 4. And so I end up getting this graph that's vertically stretched. And what I mean by that is if you imagine hands pulling on the vertical axis, stretching the graph out vertically, the graph is ultimately going to come closer to the y-axis on both sides. If we graph k of x equals 1/2 times the absolute value of x, if x is 0, k is 0. If x is 1, k is 1/2. If x is negative 1, 1/2 times 1 is 1/2. If x is 2, 1/2 times 2 is 1. Here's 2, 1 on the graph. If x is negative 2, absolute value of negative 2 is 2 times 1/2 is 1. So I end up getting a graph here, k of x, that's 1/2 times the absolute value of x, and I would say that this graph is vertically a vertical shrink compared to the original graph, and that means that if I imagine hands pulling on the vertical axis, smashing the graph vertically, I would then end up getting a graph that is pulled further away from the y-axis on both sides. In general, when it comes to vertical stretching and shrinking, let's let y equal f of x and c be a real number. Y equals c times the absolute value of x means that I've got a vertical stretch if c is greater than 1, like if c is 2, and if c is greater than 0 but less than 1, I end up getting a vertical shrink. Okay, if c is 1, which I don't have, but if c is 1, I've done nothing to affect the original graph. Okay, If I'm just multiplying by 1, that doesn't change anything. Also, if c is 0, then I've got h of x equals 0. That would be a horizontal line at a height of 0. And now, if c is negative, I could have a graph like negative 2 times the absolute value of x. And that graph would be in quadrants 3 and 4. Okay, I'd still have a vertical stretch, but it would be also flipped upside down in quadrants 3 and 4. In general, how to get the graph of the new curve, you're going to multiply the y values by c to get the new graph. Okay, so check it out right here. How I would get the graph of y equals 2 times the absolute value of x is I'm going to multiply all the y values by 2. 0, 0 is going to stay at 0, 0. 1, 1 goes to 1, 2. Negative 1, 1 goes to negative 1, 2. 2, 2 goes to 2, 4. Negative 2, 2 goes to negative 2, 4. 0, 0, when I multiply the y values by k, I would end up getting this graph. Okay, so 0, 0 is going to stay at 0, 0. 0, 1 goes to 1 half 0. Okay, right here. Negative 1, 1, when I multiply the y value by 1 half, I get negative 1, 1 half. And negative 2, 2 means that when I multiply the y value by 1 half, I get negative 2, 1. And here's 2, 1. And then negative 2, 1, 2 goes to negative 2, 1. Okay. When I hit those, the rest of these in the next video here. All right, we'll stop right there.